Hello, and welcome back for the final video in our college algebra playlist. In this video, we're going to continue our study of matrices. We're going to use matrices to solve complicated systems of linear equations. So we'll talk a little bit about what a linear equation is. Most of that gets studied in a course called linear algebra. And again, it's solving linear systems of equations. It goes a little beyond that, but that's one of the primary objects of that course. We're just going to touch on the topic here, and we're going to begin by looking at systems of three equations with three unknowns. So we'll have an x variable, a y variable, and a z variable. And we want to start by talking about what does that mean in the real world? I mean, what are we visualizing? We are going to move beyond that, and we'll look at ones which actually have four variables and four equations. Now, again, to solve it, to get a unique solution, if one exists, you have to have at least as many equations as you have variables. So if you have four variables, you need at least four equations to describe the system. Otherwise, you cannot solve it completely to get a unique solution if one exists. All right, so I'm going to share my screen with you, and we're going to get started. So now you can see my screen here, and when you're looking at my screen, you'll see first off the system of three equations with three variables, x, y, and z. Now, why do we call it linear? Linear in this sense doesn't necessarily mean line. In fact, each of these equations describes a plane in three-dimensional space. Now, what's a plane in three-dimensional space? Well, what do I have that I can use? I can use this right here. So a plane in three-dimensional space is a flat 2D surface, like a piece of paper, but a stiff piece of paper. So it's flat forever and extends in all directions, whichever way it's slanted. So we can talk about the XY plane, or we can talk about, if we're looking at the YZ plane or the XZ plane, they're all different kinds of planes. Now we're used to the XY plane, that's what we normally graph in. But in three-dimensional space, of course, a plane could be slanted like this, or it could be straight up and down. So you can think of the walls of your house as being a plane. So each wall forms a plane, the floor is a plane, the ceiling is a plane. So when we're looking at this system of three planes and we're asking ourselves, are there any points or even a single point that are on all three planes at the same time? There are lots of possibilities. Now, when we were looking at systems that only had two variables and two equations, and they were linear, there were only three possibilities. Either they were parallel lines, so there was no point in common. They were the same line, so all the points on the line were solutions, infinitely many. Or the most common, they crossed one time. When we have three planes in three-dimensional space, which is the space we live in, there are more possibilities than just those three. So let's take a look at the picture here, and let me try to describe what's happening here. Now, this one on the left is not the way that I would normally orient this. So if I were really going to orient this, what I would do is I would turn it so that it was up. So let's visualize, if you can, in your room, locate a corner of the room. So back up so that you can be this black dot here and put your back in the corner of the room. Then you have one wall on your right arm and another wall on your left arm, and you're standing on the floor. So those two walls that you're next to form two of the planes, and the floor forms a third plane. Is there a point where all three of those walls meet? And the answer is yes, right there at your feet. So right there at your feet is where the three walls come together. The floor, the wall going this way, and the wall going that way, and then you've got the floor. That means there's one point, and only one point, that is on all three walls at the same time. It's right there where they intersect. So we've got two walls coming together like this, and then we've got floor right here, and it's this point where they intersect that is our solution. So it's one unique point. Now, how would we give the point? Just like we have ordered pairs in two-dimensional space, we have ordered triples in three-dimensional space. So we would give the x coordinate, the y coordinate, and the z coordinate, and that would locate it in three-dimensional space. Now let's look at the one over here on the right. This one to me always reminds me of a pinwheel. So that toy that you played with as a kid, you blow on it and it would spin around. Or you can also think of it as a water wheel. So a water wheel has a rod through the center, and then extending from the rod up and down, it has blades. So the blades are attached to this long rod in the middle. And as it goes around, it pushes the water and it creates flow. So when we're looking at this, as it comes around, so it's got this bar here, and then it has a paddle on it like this. Each of the paddles extending through the central post forms a plane. And then the central post, actually, all of the planes touch that central post. So when we're looking here, think of the green as being a flat two-dimensional sheet of paper, but in three-dimensional space. And same for the blue and the red, but they're all intersecting each other at a line, not a single point, but at a line. Right? So we saw in the case on the left that they can intersect and give me one unique point, one ordered triple, or they could intersect at a line. Now they're not intersecting up here and they're not intersecting over here, but all the points on that line would be a solution. So we have the possibility of one unique triple or infinitely many triples. So similar to our one ordered pair, or they were the same line. Now that's also possible that there's no solution. So looking at these pictures here, these have no solution. So what could be happening? Well, let's start with the easier one, which is the one on the right. If I have three planes that are parallel to each other, then they never touch. There's no point in common. So for example, think of this as the floors of a building. So you've got the ground floor, the first floor, and the second floor. And those floors do not touch. They don't intersect or get squashed in between, right? So there's no point on each floor at the same time. You can either be on the ground floor, or you're on the first floor, or you're on the third floor, but you can't be on all three at the same time. Now, you could have two of the floors pancaked together, but if the third one is parallel, there's still no one point that's on all three at the same time. So there is another possibility that they didn't visualize here. It's kind of hard to draw because you've got to get two planes on top of each other and then the third plane separate. Let's take a look at this one right here. So what is this akin to, the one in the middle? The one in the middle is kind of like having two floors in a building. So let's say the first floor and the second floor. So we have the two floors, and then we have a wall that comes down through both floors. Well, the problem is, yes, it does intersect. So if I'm looking at the orange wall, call it a vertical wall, and it comes down and it does intersect this turquoise one at this line right here. And it does intersect, and I need a brighter color, this blue line down here, but it's not intersecting all three at the same time, and that's a problem. We're looking for points that are on all three planes at the same time. So yes, the orange and the turquoise do intersect each other. Yes, they do. So we have the orange and the turquoise intersecting here, and the orange and the blue intersecting here, but the orange, the blue, and the turquoise never cross at the same time. So there's no solution. Now this third one is more like a TP shape. They've drawn it kind of lying on its side, but you can kind of visualize, if you're looking at it like this, that you've got this TP shape right here. So you're looking at it on the edge. So these are actually planes extending away from you. When you're looking at it, and you can see it right here, you can tell that the two bluish ones, the turquoise one and the blue one, do intersect at a line right about here, okay? They do intersect there, but that bottom one does not touch it. The orange one does not touch that. Now the orange and the turquoise, they have a line of intersection was here, but the blue one doesn't touch that. And again, the blue and the orange intersect at this line right here, but the turquoise doesn't touch it. So again, we see that even though two at a time have points in common, all three do not. So there's no solution to the system. When we're looking for a solution to the system, it must satisfy all three equations for each plane. So this is what we're going to start with. And then when we go into, say, 4 variables and 4 equations, we're beyond three-dimensional space. We can't really describe it in relation to the real world because we don't live in 4 dimensions. The best we can do is maybe say it's something in three-dimensional space at a point in time where time becomes the 4th dimension. More likely, what we're looking at is a very complicated system where we want to solve something that has a lot of variables. So for example, if you are in charge of Denver International Airport and you are trying to determine, I have X number of gates, I have this number of planes coming in, I have this number of pilots ready to go, I have this number of crews ready to go, then you've got to be able to figure out how to schedule that so that you have enough time for all that. That's a very complicated problem. I mean, you've only got so many time slots, so many gates, so many pilots ready to go, so many crews ready to go. It's very complicated, all right? And you have to take the schedule into account as well. It's very complicated. But because we're looking for whole numbers of crews and whole numbers of planes and whole numbers of gates, it's easier to solve this using a system of equations. But again, you can see that we've got 4 or 5 different variables, and I'm not even taking everything into account because we also have to take into account that we've got the ground crew to prep the plane, right? So we're going to have the ground crew to prep the plane. So there are all kinds of variables that could come together to help us schedule the plane in the gate with the pilot and the crew with the ground crew to support according to the schedule that's set. All right, let's now take a look at what we're going to be doing here in section 11.6. So we have here a system of 3 equations in 3 unknowns. And notice that the middle one and the last one are not actually functions of all 3 variables. So when we're looking at these two, they're not functions of all 3. The middle one is a function of x and y, and the last one is a function of x and z. The system, however, is a function of all 3. So again, we're looking for something that's on all 3 equations at the same time. Now, when we solve a system, we need to make sure, just like when we were doing the addition elimination method, that the format of each equation is identical. So if I were going to take this one, I would probably rewrite it as 3x minus y minus z equals 0. In the middle one, now that didn't change, but the middle one I would write as x plus y plus 0z equals 5. Notice that I filled in the missing z component with a 0z. Or your other option is just to leave it blank, but to be lining them up in columns. And then the last equation, I would write 2x. I would either fill in plus 0y or leave a blank, and then I would have minus 3z equals 2. So what we're getting here is we're getting a column right here of all x values, right? And we're going to get a column right here of all y values. And the last column on the left side is going to be the z values. And then we have the equals And then we have the constants on the other side, right? This is the normal, typical way to set it up. So we go in alphabetical order, X, then Y, then Z, then equals, then constant. If we have 4 variables, it might be W, then X, then Y, then Z, then equals, then constant. Or what we often do once we get beyond 3 is we just give up on different letters because we only have 26 in the English system. And we call them X1, X2, X3, X4, X5, X6, X7, then the equals, then the constant, all right? So another thing that you want to think about when you're thinking about a linear system is that each variable, X, Y, Z, or X1, X2, X3, X4, X5, X6, they're all raised to the first power. And they're not multiplied by each other, and they're not divided by each other. So in each individual term, I have at most 1 variable, and the variable's raised to the first power. That makes it linear, right? Not linear as in line, but sort of, because linear equations have the variables raised to the first power and only 1 variable per term. And that's what we have in a linear system. So this is definitely a linear system. Now, to solve it, we form what's called an augmented matrix. So let me write that word down. That's this one right here. This is an augmented matrix. And the augmented matrix has 2 parts. The part on the left side of the long vertical bar is called the coefficient matrix. And it is exactly what it says it is. It's the coefficients of the variable terms in order from left to right and top to bottom when you do them alphabetically and when you leave holes for any missing variable. So for this one, we would have coming here, I've got a 3, a -1, and a -1. So my first row becomes 3, -1, -1. Then I have a 1, and I didn't have any Z's, so that becomes a 0. So I have 1, 1, 0 for row 2. And then I had a 2, I didn't have any Y's, so that becomes a 0, -3, 2, 0, -3. So this forms the left half of the augmented matrix. Then we draw this long vertical bar that you'll see right here. This long vertical bar is taking the place of the equal signs that we have. And then on the right side of the long vertical bar, we put our constant column. So our constants were 0, 5, 2, and this becomes 0, 5, 2. So what have we done? We've written each equation in the same form. It's got to have X first, and something for the Y column, then something for the Z column, then an equal, then a constant. Then we pulled out just the coefficients and left off the variables. I still know, however, that this column are all the X's, and this column is all the Y's, and this column is all the Z's, and this column is all the constants. Okay? Now, the systems that we're going to use to solve these, there are 2 methods we're going to cover. The book only covers 1, but we're going to cover 2 because I think the second one is more important and you should know it. So we're going to learn what's called Gaussian elimination for Leonard Gauss. Not Leonard, I'm sorry, that's Euler. What was Gauss's first name? I can't remember. All right, so we have Gauss, who is a huge mathematician. So it's called Gaussian elimination. It's basically the addition elimination method. So we're going to learn Gaussian first, and then we're going to learn another method that takes Gaussian a step further. It's called Gauss-Jordan for 2 mathematicians who came up with it. So we're going to learn Gaussian first, which will enable us to solve this system. Now, the next thing we want to do is just identify the augmented matrix and get comfortable going from the system of equations here into the augmented matrix. Okay, so here are the guidelines for, given a system of equations, how to write the augmented matrix. Again, all the X terms become column 1, Y terms become column 2, Z terms become column 3. If you are missing a term, it gets filled in with a 0. And then you draw a vertical line and you write the constants to the right of the line. But that means that your equations have to be x, then y term, then z term, then equals, then constant. The equals has to go before the constant. So let's look at problem number 1. We want to find the augmented matrix for this system. So first I verify that I've got x column. So this is my system. And I verify that I've got an x column, which I do right here. And I've got a y column, which I do right here. And then I've got my equals, which is right here. And then finally, I have the constant column, which is right here. And then I'm going to take each one of those and write down just the coefficient. So row 1 is going to become, switch colors, -1, 8, and the constant is -2. Row 2 becomes 5, -6, -3. And then to check, since we went in rows, let's go down columns. So looking at the columns, I'm going to have -1, 5, 8, -6, -2, -3. And I know I've done it right. Now, how will I write this? There's a little bit of an error here because we should have a long vertical bar there. So it should look like -1, 5, 8, -6, vertical bar for the equals, -2, -3. Right? It's bad form to leave off the long vertical bar, right? Okay, let's take a look at problem number 2 and find the augmented matrix for this system. This time, when I'm looking at this one, I see I've got an x term, a y term, a z term, the equal, and the constant for the first equation. So I know that one's in the right form. But the second one has an x term, no y term, then a z term, then the equals, then the constant. So I'm missing a term. So I'm going to rewrite it over here, and I'm going to make sure that I line them up in columns, and I'm going to leave either a blank space or a +0 for that variable term if it's missing. So I have -2y, -6z, then equals, then the constant. -3x goes under 7x, +2z goes under -6z, and then equals and -2. This time I chose to leave a blank space under the y in row 1. Then I have a 9x. I have a +5y, which goes underneath the -2y, but in row 3, I don't have a z term. So then I have the equals under the equals and 7 under the constants. And now I'm ready to go ahead and convert it into an augmented matrix. I should have a long vertical bar there. So coming across the rows, I have 7, -2, -6, -3. Row 2 is a -3. There's a blank, so 0, 2, -2. Row 3 is 9, then 5, then a blank, so 0, then 7. Okay. And again, what we're doing is we're representing them in the same format, and then we're pulling out the coefficients without the variables. The Gaussian system and the Gauss-Jordan system are going to use addition elimination method to reduce this system to something where we can identify what x, y, and z are. So this is based not on substitution, but on addition elimination. We have one more to look at, problem number 3. We want to convert the augmented matrix back to an equivalent linear system. So I identify where the long vertical bar is, and then I count the number of columns on the left side. That tells me how many variables I have. So this must be x's and this must be y's. So I've only got x and y, not x, y, and z. So this becomes -5x minus 5y equal 5, and 4x minus 2y equals -2. And this is my system, which we usually write them with the curved bracket out to the side. When you do that, it means find something that's on both at the same time. All right. Now, in order to solve the system, to get it to a form where we can say x equals this number, y equals this number, z equals this number, we need to talk about what we're allowed to do. It's based on addition elimination, which means you multiply one equation by a number and another equation by a number so that you can get the same coefficient with opposite signs on one of the variables. So we're going to be using that, and then we add those two rows together. So we're going to be using that over and over, but in matrix form. And it looks a little different in matrix form. It's actually kind of fun. I love these. So hopefully you'll enjoy it too. Now, notation is important because sometimes you forget what you're doing. So you need to write down what you're doing. Also, this gives you more partial credit with your instructor. They need to know what you're doing as well. In case you make a mistake, they can tell what the mistake was. So one thing that we're always allowed to do is interchange rows. What does that mean? Well, if I'm looking at this system right here, this is the same system as just swapping those two rows and writing row 2 as row 1 and row 1 as row 2. As you know, swapping the order that you write the equations in is not going to change the solution. So I'm always allowed to swap rows. So what we would do is we would write row 1 and a double-headed arrow, and then row 2. So an uppercase R represents row, and then the subscript is which row from before. So I swapped row 1 and row 2. That's what the double-headed arrow is. Row 1 became row 2, row 2 became row 1. So this is interchanging rows, and this is always allowed. Will not change the solutions. Multiply a row by a constant. So if I want to do that, I could take, well, let's look at these that I've got right here. I might decide that I want to take row 1 and, or actually, yeah, let's take row 1. And to get the coefficients of x to be the same, I could multiply, well, let's not do that one. Let's do the y. Let's get rid of the y. I can multiply row 1 by -5 and put it back into row 1. And I could take row 2 and I could multiply it by 2. And I could put it back into row 2. Notice those arrows are not double-headed because I'm not swapping each with the other. I'm actually replacing row 1 with -5 times row 1. So what would that lead to? Well, I would take the 4x and multiply by -5, which would give me a -20x. I think I can see what's going to happen here. -5 times -2 would give me a +10y. And then I would have the -5 times -2, which would give me a 10. And then when I did this on the second row, I would get a -10x. And then I would get -10y. And then I would have equals 10. Now, in a system of equations, instead of, this is how you would solve it. But if I were doing matrices, let's take off the pieces and show what it would look like in matrix form. So we would lose the equals, and instead we get the vertical bar, and we would lose the variables, and we would just have the numbers. So let's write this one down here in the right format for matrices. Bar. We would lose these numbers right here, right? Does everybody see kind of what's happening? All right. Now, the last thing we're allowed to do is add the product of a row multiplied by a constant to another row. So I can multiply any row by any constant I want. You know, in equations, if you multiply both sides by 2, it doesn't change the solution, right? So that previous step is not going to change the solution. This next step is the actual addition elimination method. So for my next step, what I'm going to do is I'm just going to take row 1 and I'm going to add it to row 2, and I'm going to put it back into row 2. right? I could put it back into row 1 or I can put it into row 2, but I'm going to put it back into row 2. So notice that row 1's not on the right side of an arrow, so it doesn't actually change. Let me scroll down a little bit so I have some space. So row 1 stays negative 20, 10, 10. But row 2 now, I'm going to add negative 20 and negative 10, and that's going to give me a negative 30. And then this one coming down, if I added the 10 and the negative 10, I would get 0. And 10 plus 10 would give me 20. Now, how does this help me solve the equation? The actual thing I would do for Gaussian elimination then would be to swap rows 1 and 2 again and try to get it into what's called row echelon form, right? So let me show you what that looks like. The next thing that I would do is I would swap the rows again. So I'm swapping row 1 and row 2. So I need a double-headed arrow. And then I'm going to have negative 30, 0, 20, and I'm running out of space. So negative 20, 10, and 10. Well, I guess I could leave it the other way. That would be okay. What is this row, though, right here? What information is this giving me? I might not swap the rows. I might just leave it. What is that telling me? Well, it's actually giving you information. It's telling you that negative 30x plus 0y equals 20. Well, then I can divide both sides by negative 30, and I have x equals negative 2 over 3. And then I can take that solution and I can put it into the second row to find the solution, right? So this is a part of Gaussian elimination and also a part of Gauss-Jordan elimination. Now, Gauss-Jordan goes further. Gauss-Jordan ends up getting all ones on the main diagonal and zeros off the main diagonal so that you can just say x is this, y is this, z is this, right? So we'll take a look at both. First, though, we need to talk about row echelon form. So it's kind of a weird word, echelon. So we have this row echelon form, and really what we should have here is we should have a long vertical bar and a constant on the other side, which it does not. So I'm going to fix that right now because that should definitely be there. So we should have a vertical bar, and then we should have a constant 1, constant 2, constant 3. I don't know what they are, but they're the constants in the equation on the other side of the equals. Row echelon form for the coefficient matrix side, and that's on the left side of that long vertical bar, has a couple of rules. Now there's something called row echelon, which is this, and then reduced row echelon. Now the book didn't get into reduced row echelon, but we are going to cover it because Gauss-Jordan is actually more commonly used than Gaussian elimination. So what are the rules? Here is the first rule. In any non-zero row, the first non-zero number is 1. It's called a leading 1. Now, if you have a row that's all zeros, it needs to drop to the bottom. Remember, we're allowed to swap any 2 rows. So if one row just zeroes out, 0 all the way across, it goes all the way to the very bottom. Then, in any row that's not all zeros, the first number in the row should be a 1. So, for example, if we want to come back up here to the one that we had up here, let me start with this format right here. So I'm going to start with the negative 20, 10, 10, negative 30, 0, 20. Okay, so I don't have any row that's all zeros, but the first number in any row should be a 1. So what I might do next is divide out so that I can get a 1 in one of these rows. So for example, on this one up here, to make this first point right here a 1, I would have to divide by a negative 20. So I could take row 1 divided by negative 20, put it back into row 1. I'm not doing anything to row 2, so this becomes a 1. 10 divided by negative 20 is negative 1/2. And this is also a negative 1/2, right? Then I have negative 30, 0, and 20. Although I'll be honest with you, and maybe we should go ahead and do this. I would look at this and go, oh, well, row 2 has a constant factor of 10. So let's just divide everything by 10 and put it back into row 2. And that would eliminate those. And I would end up with this. So I have a non-zero row, and the first number is a 1. It's called a leading one. So I fixed this first row, but the problem is I haven't fixed the second row. So if I'm going to fix the second row, I need to think about what I want to do. But in this particular case, I would actually probably swap the 2 rows. I'd like to have the 0 be in the first row. So I'm going to swap rows 1 and row 2. And I'm going to have negative 3, 0, 2, 1, negative 1/2, negative 1/2. And now I've got a problem again because this is not a positive 1. So I want to get rid of, and sometimes we do these in different orders. Any leading 1 is below and to the right of any previous leading 1. And any leading 1 has zeros below it in the column. So I'm going to make this negative 3 a 1, but before I do that, I want to get rid of the 1 in the row below it. So I would take row 2, and I would multiply row 2 by 3, and I would add to that row 1. Now, some students like to go ahead and write this out. So 3 times row 2 would be 3, negative 3/2, negative 3/2, and they're going to add row 1 to it. There's row 1, row 2. And when I add them together, I'm going to get my new row 2. So row 1 is not going to change, but row 2 is going to become 0, negative 3/2, and 2 becomes 4/2 minus 3/2 is 1/2. So I get 0, negative 3/2, 1/2. And this is my new matrix. Now I want to fix row 1 so that in row 1, I have a 1 in the first position because now I've got a 0 underneath it. So I'm going to take row 1 and I'm going to divide by negative 3 and put it back into row 1. Now, looking at row 2, I've got a 0, which will be under that. So let's go ahead and finish that part of it. So I've got 1, 0 divided by negative 3 is still 0. 2 divided by negative 3 is a negative 2/3. My negative on there. There's my long vertical bar. Now, I don't like the fraction in row 2. It says to be in row echelon form that the first number in the row needs to be a 1. So to get this to be a 1, I should multiply by a negative 2/3. So I'm going to take row 2 and I'm going to multiply by a negative 2/3. So the 2's cancel and the 3's cancel. And I'm going to put it back into row 2. So I get 0. And then I'm going to get a positive 1. And then you might want to come over here and write that down somewhere. You have negative 2/3 times 1/2. The 2's cancel. And you get negative 1/3. Now, this is actually not only in row echelon, but in reduced row echelon form, where both above and below the leading ones, we have zeros. And if I look at this and I put it back into a system of equations, this says x equals negative 2/3, y equals negative 1/3, which tells me that I have my solution, my ordered pair, negative 2/3, negative 1/3. So let's go over again what row echelon form is, and then we'll compare it to reduced row echelon. In row echelon, the first number in a non-zero row needs to be a 1. So right here, this needs to be a 1. Okay. Then below that, in the rest of the column, you need to have all zeros. So below any leading 1, I've got to have all zeros. Looking at the next row, I will have my first 1 be to the right of the 1 in the row above it. If they're not, I just switch rows. So they go in a stair step coming backwards down the main diagonal. So again, I need to have a leading 1 here, and I need to have a 0 in the row below it, in the column below it. And then my third one, I've got to have the leading 1 be further to the right than the ones above it. And that gives me this one here. And this is what we call row echelon form. Now, how does this help? Let me give you an example here. So if we're looking at this right here, we're looking at this particular problem in row echelon form. I know column 1 represents X's, column 2 represents Y's, and column 3 represents Z's. And these are all constants. So this tells me from the third equation that I have that Z is equal to whatever constant 3 is, 5 or 7, whatever it is. Row 2 tells me that Y plus the constant D is equal to C2. And the first row tells me that X plus A times Y plus B times Z equals constant 1, right? This is what's called Gaussian elimination. I know what Z is, it's C3, it's a constant. Then I can use that to substitute, I lost my Z here. I can use that to substitute for Z in equation 2 in row 2 to find Y, then I can substitute for Z and Y in row 1 to find X. Okay, let's talk about reduced row echelon form. So again, in row echelon form, I have 1s down the main diagonal and 0s below it. So the main diagonal goes from upper left to lower right, and then below that I have all zeros. Above it, I may or may not have zeros, and then I'll have constants over here. Some may be 0, some may not. What's reduced row echelon form, also called row canonical form? It says I'm going to have 1s coming down the main diagonal, or if I have one off the main diagonal, it's further to the right than the ones above it. And I'm going to have zeros above and below those 1s. So this one is in reduced row echelon form. Now, when you get to reduced row echelon form, it can come from an equation like this, and it ends up in an equation like this. And you can see here we have a 3 by 3 coefficient matrix, giving us overall a 3 by 4 when we include the constant column. This then tells me X equals 2, Y equals -1, and Z equals 3. So reading off the solutions from reduced row echelon form is a snap. It's super easy. And it only requires a few additional steps that row echelon form does not. So let's start with something relatively straightforward and not difficult, because this is a confusing process. You've never done it before, so it's going to take some while to get used to it. So on this one, I look at it and I say, well, okay, is it in row echelon form? I've got a 1 here, and I've got a 0 below it. So I know that that is, so far, that is in row echelon form. And then I'm looking at row 2, but I need to have a 1 as the first number. So what I'm going to do is I'm going to take row 2, and I'm going to divide row 2 by 2 and put it back into row 2. I'm not going to do anything to row 1. So row 1 stays 0, 1, 0, 3. Row 2 becomes 0, 1, 3. Now, I'm actually in reduced row echelon form because I've got leading 1s in each row. The row on the bottom, the 1 is further to the right than the row above it. and I've got zeros both above and below my leading ones. Then I can read the solution directly because the first column are the x's and the second column are the y's, and these are all constants on the far right in the augmented section. This says x equals 3 and y equals 3, all right? Because I don't have a y term in row 1 and I don't have an x term in row 2. Okay, let's take a look at one that's not as simple as the one before. Not that it's simple, but this one is more difficult. So in this one, and again, I want to emphasize that there are so many different ways to solve this. I can have a class of 24 students and 24 different ways that they approached it. So because you solve it differently than me doesn't mean you're wrong. It just means you're looking at it from a different viewpoint. As long as you come up with the same solutions, you're good. So I'm going to look at this one, and I know that I want this first one to be a +1, but I also know that below it, I want that to go away. Because these already have opposite signs, before I make that first one a 1, I'm going to use addition elimination to get rid of the 3. So I'm going to take 3 times row 1. I'm going to add it to row 2, and I'm going to put it back into row 2. So 3 times row 1 would be -3. 2 times 3 would be 6, and 3 times 4 would be 12, right? And then I'm going to take row 2 without change. So 3, -4, 4. And then when I add these together, I get 0 to 16. So row 1 did not change. It stayed -1, 2, and then 4. But row 2 is now 0 to 16. Now I want to go ahead and I want to fix this first position here where I have the -1 and make it a +1. I also want to fix row 2. I know my first number in the row should be further to the right, and it is, but it needs to be a 1. So I want to multiply row 1 by a -1 and divide row 2 by 2. And I can do both on the same step. So I'm going to take negative row 1 and put it back into row 1. And I'm going to take row 2 and divide by 2 and put it back into row 2. The directions are important so that you remember what you're doing, and it helps your brain to process while you're going through the steps. And it also helps your professor to figure out what you were trying to do in case you accidentally made an error and came up with the wrong solution. So now what we're going to do is we're going to look at this one from a Gaussian elimination perspective. And I'm going to take this, now that I have it in row echelon form, I've got a 1 in row 1 in the 1, 1 position. I've got a 0 below this main diagonal. I've got a 1 over here as my first one. And so I'm going to rewrite this as x minus 2y equals -4, y equals 8. All right, so the second row tells me what the y is. It's 8. And then I can take that and use substitution into the first equation. So I'm going to call this 1, I'm going to call this 2, and I'm going to substitute y equals 8 in equation 1. So this gives me x, let me come over here. This gives me x minus 2 times 8 equals -4. So this leads to x minus 16 equal -4. Add 16 to both sides. I'm getting x equals 12. So my solution would be, as an ordered pair, 12, 8. Right? So that would be the solution to the problem. This is using Gaussian elimination. Now, could I go to reduced row echelon, where both below and above the leading ones I have zeros? And then would it be easier to find the solution? Yes, I can do that. So what I'm going to do is I'm going to take the matrix, the last matrix that we had, which is this one here, and I'm going to take what's in row 2, and I'm going to use this 1 with addition elimination to eliminate the -2. It won't mess up this one because I have a 0 here. So I'm going to take 2, not -2, but 2 times row 2 plus row 1 back into row 1. So I need to scroll down so I have some space. 2 times row 2, well, 2 times 0 is still 0. 2 times 1 is 2. 2 times 8 is 16. And then row 1 is 1, -2, -4. And when I add these together, I get 1, 0, 12. So my new row 1 is 1, 0, 12. And row 2 did not change, long vertical bar. And notice that we got the same solution. I can read this one directly. It becomes x equals 12, y equals 8, and that would be an ordered pair. It's an ordered triple if you have 3 variables, and ordered quadruple if you have 4. Now, this method is called Gauss-Jordan. This method is called Gaussian. So let me write those down. This is the Gauss-Jordan elimination method. And this one over here is Gaussian elimination. I do not have a preference as to which methods my students use. You should understand how to do both, but I do not mind if you do Gauss-Jordan instead of Gaussian or Gaussian instead of Gauss-Jordan, so long as you understand the process. Let's now solve this system of equations. So first we check the format. X first, then y, then equals, then constant. X first, then y, then equals, then constant. They match. Now we write the augmented matrix. So we're going to have the coefficient matrix on the left. So 3, 2, long vertical bar, then 2, 6, 1, and 1. Check in columns, 3, 6, 2, 1, 2, 1. All right, looks good. Now I know that I want to have a 1 in the upper left in the 1, 1 position. But before I do that, I'm going to see if I can get rid of some stuff. So if I'm looking at row 1, I know if I multiply row 1 by -2, I'll get a -6. And then I add it to row 2 to get rid of that. So usually we do the addition elimination before we get the 1s, but not always. It just depends. So I'm going to take -2 times row 1, add it to row 2, and put it back into row 2. -2 times row 1 gives me a -6, -4, -4. Row 2 does not change until I've added them together, and I get 0, -3, -3. So now I have 3, 2, 2, and 0, -3, -3, right? So I like to avoid fractions. So if I'm looking at this one, I can tell that if I divide this by 3, this is going to become a 2/3. So I'm going to wait and do that at the very, very end. So the next thing I'm going to do is I'm going to look at this and I'm going to go, well, this is negative and this is positive. So if I multiply this one by 2 and this one by 3, this will be 6 and this will be -6. And then I can add row 2 to row 1 to get rid of this 2, right? This would be Gauss-Jordan method. If you want to do Gaussian, the next step that you should do would be to divide row 2 by -3 and row 1 by 3. So we'll do each one separately. So Gaussian, I would take row 1, divide by 3, put it back into row 1, and I would take row 2, divide by -3, and put it back into row 2. So this would give me 1, 2/3, 2/3, and then I would have 0, 1, 1, right? Now Gaussian, you have to go back to the system of equations. So I get x plus 2/3 y equals 2/3. And the second equation, y equals 1. Then I can substitute the 1 back into the first row, which will give me x plus 2/3 times 1, which is 2/3, equal to 2/3, which basically means x equals 0. So this would give me 0, 1. But you're going back to the system of equations. In Gauss-Jordan, you do not. Right? In Gauss-Jordan, you take it all the way down to a reduced row echelon form. So I would, in this case, take 3 times row 1 plus 2 times row 2. I don't want it to go into row 2. That'll mess up that 0 that I worked so hard to get. I want to get rid of the 2 in row 1. So this goes back into row 1. So this is going to be 3 times row 1 would be a 9, 6, 6. 2 times row 2 would be a 0, negative 6, negative 6. And when I add those together, I get 9, 0, 0. So now my row 1 becomes 9, 0, 0. And my row 2 is 0, negative 3, negative 3. And now that I have this format where I've got zeros above and below the leading number, now I can make them into ones. So I'm going to take row 1, divide by 9, put it back into row 1. I'm going to take row 2, divide by negative 3, put it back into row 2. So this is going to give me 1, 0, 0, 0, 1, 1, which gives me, again, x equals 0. Doesn't look much like an x, does it? X equals 0, y equals 1, which is the same solution I got over here. Okay, now we're going to expand our study a little bit from systems of 2 variables and 2 equations to 3 variables and 3 equations. It gets more complicated. Now, again, if we're looking at 3 variables and 3 equations, then we're going to have a square matrix. So we're trying to get ones down the main diagonal as much as we can, but at a minimum, each leading one needs to be further to the right than the one above it. For these 2 problems, we just want to verify whether or not it's a solution. Now, remember, to be a solution, you have to be able to plug it into all 3 equations at the same time and get some kind of true statement. If you get a false, it's not on that line. And in this case, they're not lines, they're actually planes. So we're going to check, right? So over here on this one, I want to check if -5 to -6 is a solution to the system. So I have 2 times -5 minus 5 times 2 minus 6 times -6. And it's a question, does it equal 16? So this gives me -10 minus 10, which is a -20. And I'm in trouble because -20 plus 30, oh no, that works. So I have -20 plus 36. Yeah, that does equal 16. So it's on that plane. That doesn't mean it's a solution to the system. It's got to be on the other 2 as well. So I'm checking in equation 1, and now I'm going to check in equation 2. So I have -4 times -5 plus 3 times 2 plus 6 times -6. Does this equal -10? Well, this would give me 20 plus 6, which is 26 minus 36. And yes, that is -10. So it's on that plane as well. Is it on all 3? So plugging it into the last one, I have -2 times -5 minus 3 times 2 minus 2 times -6. Does that equal 16? So this is my question. And this would give me 10 minus 6, which is 4, plus 12, which is 16. Yes, it is. So it is a solution to the system. What does that mean? If I were to augment this and row reduce it, that's what it's called using the Gaussian elimination method or Gauss-Jordan method, I would get that x equal -5, y equal 2, and z equal -6. Now what I'd like for you to do is check the solution in the second problem on the right. Pause the video, work it out, then turn it back on to compare. You'll notice I don't have a lot of work written down because when I checked it in the first equation, it failed. 35 plus 6 is 41, and 41 minus 8 is not 28, right? So when I'm looking at this, I got 33 equals 28, which is false. That's not true. 33 does not equal 28. And that means that that point is not on the first equation. It doesn't matter if it's on the other two. It's not on the first one. It's not a solution to the system. I can stop right there. Let's now turn our attention to actually solving one of these more complicated three-variable, three-equation systems. So the first thing I'm going to do is write it in augmented form. So my first equation has 1 for the coefficient of x, 2 for the coefficient of y, 2 for the coefficient of z, and a -1 for the constant. In equation 2, I have -1 for the coefficient of x, -1 for the coefficient of y, but I have no z term. That means I have to fill that in with a 0. And the constant term is also -1. Then I have, for the last one, 3 is the coefficient of x, 6 is the coefficient of y, 7 is the coefficient of z, and 2 is the constant. Now, when we're looking at these, what we often want to do is we want to find one that has a 1 or a -1 coefficient to knock out 2 of the first elements in the rows. So we're trying to get the first column fixed. So when I'm done, I want to be able to look at this column right here and have one number in the column and 2 zeros. And you'll notice that I've got this -1 in the middle. So that is the one that I'm going to use. So I like having the +1 in row 1, so I don't want to mess that up. But what I can do is I can take row 1, add it to row 2, and put it back into row 2. Now, if I do that, I have 1, 2, 2, -1, and row 2 is -1, -1, 0, -1. This is addition elimination. When I add them together, I get a new row 2. I'm not going to change row 1, so it stays 1, 2, 2, 2, -1. Row 2 is now 0, 1, 2, -2. All right. Now, the next thing I want to do is I need to get rid of that 3, and I can do it at the same time. I'm going to instead take the old row 2, multiply it by 3, and add it to row 3. So I'm going to be taking old row 2, and I'm going to multiply by 3, add to row 3, and put it back into row 3. So -1 times 3 gives me -3. 3 times -1 gives me -3. 0 times 3 gives me a 0, and -1 times 3 again is -3. And then my row 3 was 3, 6, 7, and 2. Add them together for a new row 3, 0, 3, 7, -1. All right. Now, have I fixed column 1? I have one number and 2 zeros. Whether or not I put a 1 there depends on whether or not it would introduce fractions. If it introduces fractions, wait and do it at the very end. Now I need to fix column 2. In column 2, and row 2, I need to have a leading 1, which I have in row 2. So I kind of like that. I'm going to leave that alone. For Gaussian elimination, I need to use the 1 to get rid of the 3. So I'm going to take row 2, my new row 2, and I'm going to multiply by -3 and add it to row 3 and put it back into row 3. So I'm going to have 0, -3, -6, 6, plus 0, 3, 7, -1. Hopefully I haven't made any mistakes so far. It's very easy to make careless mistakes. Work slowly and carefully. So this gives me 0, 0, 1, 5. So now I've got 1, 2, 2, -1, 0, 1, 2, -2, 0, 0, 1, 5. For Gaussian elimination, I would stop right here. I have enough to finish solving the equation because my last line tells me that z equals 5. So for Gaussian, I would stop here. And I'm going to need a lot more space. I did not leave enough room. So I would rewrite the system. X plus 2y plus 2z equals -1. No x, 1y plus 2z equals -2, and z equals 5. So this is equation 1, this is equation 2, and this is equation 3. I'm going to sub z equals 5 into equation 2 to find the y value. So this would give me y plus 2 times 5 equals -2. So I get y plus 10 equals -2, or y equals -12. And then I'm going to sub z equals 5 and y equals -12 in equation 1. So this would give me x plus 2 times -12 plus 2 times 5 equal -1. So this gives me x minus 24 plus 10 equals -1. So I would end up with x minus 14 equals -1. When I add 14, I get x equals 13. So my ordered triple in order is 13, -12, 5. Okay? This is how you would solve it with Gaussian elimination. With Gauss-Jordan elimination, you don't stop at row echelon form. Once you have row echelon form, you use the leading constant in each row to eliminate the ones above it. And we move from the left to the right. So for Gauss-Jordan, to continue, I would use this one to get rid of that 2. So I would take row 2 and I would multiply by a -2, add it to row 1 and put it back into row 1. So I would have 0, -2, -4, 4, added to row 1, 0, 2, 2, -1. And that would give me 1. It doesn't mess up my leading 1 because I have 0 there. 0, -2, 3. So now I've got my new matrix. 1, 0, -2, 3. My old row 2, 0, 1, 2, -2. And my old row 3, 0, 0, 1, 5. Now I need to use row 3 to eliminate the 2 and the -2. You can't use rows 1 and 2. You'll mess up one of the zeros. You have to use the one that only has 1 in it now. So I'm going to be using this one now in order to eliminate both of those. So now what I'm going to have is I'm going to take -2 row 3 plus row 2 back into row 2. And I'm going to take to row 3 plus row 1 back into row 1. Okay, so each one in turn, -2 times row 3 is going to be 0, 0, -2, -10. Plus row 2 is going to be 0, 1, 2, -2. So my new row 2 is 0, 1, 0, -12. Then I'm going to have 2 times row 3 plus row 1 back into row 1. So 2 times row 3 would be, and I need some space here, 0, 0, 2, 10. And my row 1 is 1, 0, -2, 3. And this will give me 1, 0, 0, 13. So when I put it back into a single matrix, my new row 1 is 1, 0, 0, 13. My new row 2 is 0, 1, 0, -12, and my row 3 did not change. This is reduced row echelon form because I have a leading 1 in each row, and both above and below it, I have zeros. And this just reads x equals 13, y equals -12, and z equals 5. So whichever method you find easier to do or makes more sense to you, use that method. Now let's take a look at a different one. So we've got a system right here. And what I would like you to do is go ahead and pause the video, augment the system, and start to solve it. If you encounter something unusual or something weird happens, turn the video back on and we'll talk about why. Okay, now something weird should have happened. Let's go through and then we'll discuss what happened and what it means. So in this case, I went ahead and augmented the matrix. I noticed that row 1 to start with had all negatives on it, but the other numbers in column 1 were also negative. So I chose to go ahead and multiply row 1 by -1 to make it all positive so that I could have this first one be positive to eliminate the other 2. Then I took 2 times row 1 plus row 2 and put it back in row 2, which led to this one here. I took 3 times row 1 and added it to row 3 to get rid of the -6 here. And that gave me this matrix that you see here. Once I have fixed column 1, then I need to use the leading 1 or the leading position in row 2, column 2. So now I need to use the 11 to eliminate the 3 and the 22. If I thought this number were better, I could swap rows 2 and 3, but not row 1. That's the one with the constant in the first position. It stays row 1. So I chose to leave the 11 where it is and to take the 11 and eliminate the 3 and 22. To get rid of the 3 is a lot more work. I need to multiply row 2 by -3 or 3 and row 1 by 11 with the opposite sign. So I took 3 times row 2 minus 11 times row 1 and put it back in row 1. It did mess up the number a little bit, making it negative again, but that's easily fixed towards the end. Then to get rid of the 22, I multiplied row 2 by -2 and added it to row 3, which gave me the 0, 0, 0, 1. That right there was a signal to stop. Let's think about what that bottom one means. If I were to take that out and write it as an equation, this last line where I have all zeros on the coefficient side, but not 0 on the other side, says that 0 equals 1, which we know this isn't true. That's false. And because it's false, it means that this is an inconsistent system. There is no solution. There is no single point that's on all 3 planes at the same time. There's no solution. So we're solving, and we got all the zeros on the coefficient side to cancel, but we didn't have 0 on the right. Now, if we had 0 on both sides, it would be okay. It would mean there is at least one solution. But in this case, we had 0 equal to 1, which is false. There are no solutions. So we stop there. Let's now look at the next system. Use whichever method you prefer, and let's see what happens. Again, there could be no solution if we get a false statement. If everything in a row zeroes out, we could end up with infinitely many solutions. So pause the video, work it out, turn it back on, and we'll compare our work. So how did you enjoy doing that problem? I will admit to you that I made 2 careless mistakes. I lost 2 negatives, and because of that, the whole thing just crashed and burned. I was getting awful numbers, and I thought, oh, I think I've got a mistake. So I went back to the beginning and carefully traced through, especially the negatives, and that's when I found that I lost 2 negatives, and I was able to fix my work. On this problem, you should have gotten the solution -1, -2, -6. I chose to go ahead and reduce it all the way to reduced row echelon form so I could easily pick out the answers. I'll scroll down slowly so that you can see my solutions, but we'll not go through them step by step as we've done before. So you may want to pause the video occasionally so that you can see each step. Notice that I did reach a point where I had 145 and -870 in a row. Now, I knew those numbers were crazy, so I thought, I wonder if 870 is divisible by 145 evenly, and I discovered it was. So if it's evenly divisible, go ahead and divide by it, and that will make your numbers more reasonable. Anytime you can tell you have a common multiple in a row, divide by the multiple to make your numbers smaller. And here's the final steps to get to the final solution. Again, you could have stopped when you got into row echelon form and back substituted so that you could find the solutions in Gaussian elimination. Now, I should say at this point that there are technology ways of solving these problems. Obviously, if we have a very complex problem like the airport problem, we don't solve those by hand. You can use a graphing calculator, and there are multiple videos out there to show you how to do that. But we're kind of getting away from graphing calculators in a lot of ways. So I want to show you a more up-to-date method of doing that, and that's using what's known as an online calculator. So the one that I recommend for matrices is Symbol Lab. So Symbol Lab, but with just one L. So just go into Google or whatever search engine you use, and you'll notice it popped up. And so I'm going to put in Symbol Lab. And it says Symbol Lab Math Solver, blah, blah, blah. So I'm just going to click on that. And it's going to pop up. And I'm going to click on, well, let's see. This is not the one I wanted. So let's go back. And let's go to step-by-step calculator. That's the one I want, step-by-step. Now, matrices are a huge part of what is studied in linear algebra. So they're under the linear algebra tab. So in the top bar, click on linear algebra and then matrices. And what we've been using is either Gaussian elimination or Gauss-Jordan. Now, on online calculators, they're going to use Gauss-Jordan because it gets all the way to the solution. So you're going to come over here now to the drop-down menu, which shows you matrices. And yes, you can add, subtract, and multiply here. And we're going to click on Gauss-Jordan. Now, you could put it in row echelon form, but we're going to go to Gauss-Jordan. We're going to click on that, and it's going to put the words Gauss-Jordan at the beginning. Now we need to enter in our augmented matrix. So I'm going to click on this, and our matrix was a 3x3 coefficient matrix plus the constant matrix. And I'm going to click there, and then it will allow you to enter the values, tabbing in between. So you click tab to go from one to the next to the next. So I'm going to pull this over to the side and scroll up. So I would put in 3, tab, -3, tab, -2, tab, 15, tab, -4, tab, -3, tab, 6, tab, negative 26, tab, negative 6, tab 2, tab negative 1, tab 8, right? Once I get them all in there, then I can either hit enter or I can click on go, and it's going to solve it very quickly, pretty much instantaneously. And it's going to give us the solutions in reduced row echelon form here, which tells us X is equal to negative 1, Y is equal to negative 2, and Z is equal to negative 6, which is the same solution we got before. So I don't want you to get frustrated if you find that you're making lots of careless mistakes and you're just, it's driving you crazy. You can use technology to solve these as well. You do need to follow the steps on a simpler one to be able to solve it by hand, but on the more complicated ones, let's use technology. So now let's go up here and let's solve this one right here. So we have this system and let's see what happens. So I'm going to scroll this over to the side. And I'm going to scroll back up and I'm going to highlight these and I'm going to change my numbers. So I have negative 6, tab, and I need to eliminate what was in there. So I've got 2. Let's see if it'll get rid of the rest of it. Negative 6. So coming over, negative 2 becomes negative 6, tab, 22. Tab, the negative 4 needs to become a negative 18. The negative 3 needs to become a negative 2. And the negative 26 just needs to be a negative 2. Make sure you put them in correctly or it obviously will not work. And that needs to become negative 42. And then this needs to be a negative 2, so just add the negative. And then this needs to be negative 30. And finally, the last one needs to be 18, right? So then I can hit enter or go, and it's going to take a moment and calculate the solution for me. So then I'm going to scroll down, and when I come down here, you'll see that I have the solutions down here. I've got Z equals 0, Y equals 17 halves, and X equals a negative 5, 6. So this one would not have been so much fun to try to do by hand because of the fractions. All right. Let's now take a look at a couple of applied problems and see how we can put these into matrix format in order to solve these very complicated application problems. So as we do with all application problems, the first time we're just going to read the problem and get a vague idea of what we're looking for and what kind of problem it is. It says a bag of mixed nuts contains cashews, pistachios, and almonds. There are 3,000 total nuts. If you count them, there are 3,000 in the bag, and there are 400 fewer almonds than pistachios. So if there are 800 pistachios, there are 400 almonds, 400 less. Cashews weigh 1 gram, which is a little less than a paperclip. Pistachios weigh 2 grams, which is about a big paperclip, and almonds weigh 4 grams. If the bag weighs 3.8 kilograms, they just switched the unit there. That's a no-no. Find out how many of each type of nut is in the bag. Okay, well, they want to know the number of cashews, the number of pistachios, writing, and the number of almonds, like counting them, how many are there? Now, I could let cashews be X, and I could let pistachios, the number be Y, and the number of almonds be Z. Going back to the beginning, let's pull apart the words into subject phrase, verb phrase, prepositional phrases, subordinate clauses, conjunctions, in punctuation, anything that separates the sentence into parts of speech. a bag of mixed nuts contains cashews, pistachios, and almonds. Okay, I've got that, but that's not mathematics. There's nothing to translate there. There are 3,000 total nuts in the bag. That is mathematics. 3,000 total means when I add stuff together, I get 3,000. That equation is going to be x plus y plus z equals 3,000. All right, so that part of that sentence translates into this equation. And there are 400 fewer almonds than pistachios. Okay, now how can I write that down? Well, if I take pistachios and I subtract the almonds, I should have 400. So pistachios was y and almonds is z. So if I take the number of pistachios and I subtract the number of almonds, I should come up with 400. And notice that I've lined them up in the columns where they belong. Now let's continue to the last sentence. Cashews weigh 1 gram, pistachios weigh 2 grams, and almonds weigh 4 grams. Okay, well, it sounds like math, but there's really no equation to write down. But the next sentence says, if the bag weighs 3.8 kilograms, so each single cashew weighs 1 gram. So if I have 5 cashews, then I have 5 grams. So I'm going to take the number of cashews and I'm going to multiply by 1, and that will give me the number of grams that are due to cashews. Now, what about pistachios? They're a little heavier. They weigh 2 grams each. And I have Y number of pistachios, each 2 grams. So if I add to that my 2 grams times my pistachios, that's the total weight of those 2 types of nuts in grams. Now I want to take the almonds, which weigh 4 grams a piece, and I'm going to add that in. So 4 grams times each almond, which is Z. And this should give me total number of grams. Now the problem is, what it said was kilograms. Now kilograms are equal to 1,000 grams. So I need to convert the 3.8 kilograms into grams. So 3.8 kilograms is equal to 3,800 grams. So this is equal to 3,800 because I need the units on the left and the units on the right to match. Now I've got 3 equations and 3 unknowns, so I should be able to solve it if there's a solution. So go ahead and pause the video, either use an online calculator or you can do it by hand, and then come back when you think you've got the answer. So how did you do? My guess is you used the online calculator and it gave you the answer very quickly, which is what I did, so I can certainly relate. Solving a 3-variable system is quite complicated and takes a lot of work. The numbers can get a little unwieldy and large, or negatives can run around and get lost. So using an online integral calculator is not a bad idea. So when we're looking at this one, we ended up with 2,400 cashews, 500 pistachios, and 100 almonds. Now let's take a look at the last problem in our sequence, and we'll again set up the equations, then pause the video to work it out. In this one, it says an animal shelter has a total of 120 animals comprised of cats, dogs, and rabbits. If the number of rabbits is 5 less than 1/2 the number of cats, and there are 20 more cats than dogs, how many of each animal are at the shelter? Again, we need to let the number of each animal be one of our variables. So I'm going to let the number of cats equal X, and the number of dogs will equal Y, and the number of rabbits will equal Z. Then I'm going to go back to the beginning of the words, pull it apart into the parts of speech, roughly every 2 to 3 words, and see if there's something mathematical that needs to be translated. So when I'm looking at this, it says an animal shelter, nothing to translate, has a total, something mathematical is coming, of 120 animals comprised of cats, dogs, and rabbits. So this must mean that I have x plus y plus z equal to 120. Now the next sentence reads, if the number of rabbits, what is the number of rabbits? Z. So I'm going to write that down. Z is, that's equals, 5 less than, that's something minus 5. 1/2 the number of cats. Well, the number of cats is x, and 1/2 of that would be 1/2 x, all right? And there are 20 more cats than dogs. So if I take cats and I subtract dogs, I should get 20 because there are more cats than dogs. So that would be x minus y equals 20. Now I have a problem with this system. The forms don't match. The first equation and third equation are good to go, but the middle equation is not. But the rules that we can apply to matrices apply to these equations as well. I can move the 1/2 x to the left by subtracting, and I can also multiply that entire equation by 2 to get rid of the fraction. So I'm going to take this equation number 2, and I'm going to multiply by 2 first to get 2z equals x minus 10. And then I'm going to move the x to the left, and I'm going to write this as negative x plus 2z equals negative 10. So now when we put it into our augmented system to solve it, we should have as row 1, 1, 1, 1, 120. And in row 2, we should have negative 1, 0, since there's no y term, 2, negative 10, and then 1, negative 1, 0, since there's no z term, and 20. Now keep in mind that we're talking about whole animals here. So if we put fractional answers, this application problem doesn't have a solution. You can't have part of a cat or a dog or a rabbit. So go ahead, pause the video, work it out, and turn it back on, and we'll compare our results. How'd you do? In this case, we find that there are 58 cats, 38 dogs, and 24 rabbits, which makes total sense. Now there's one more type of problem I want to do for you, and then we will be done with our video series for college algebra. The one system we have not seen yet is a dependent system. So let me set one up, and we'll take a look at what happens when we have these 3 planes intersecting at a line. So there are infinitely many solutions. So we've come to the final problem on our final video in this college algebra playlist. Let's take a look now at the equation you see here in the gray block. I went ahead and augmented the matrix and worked this one out by hand so you could see what will happen. In this case, I used negative 2 times row 1 plus row 2 to get rid of the 4 in row 2. And I used negative 2 times row 3 plus row 1 to eliminate the 1 in row 3. And this created a row of entirely zeros. But it is true that 0 equals 0. So it's not an inconsistent system. Now, if we have an all 0 row, it needs to drop to the bottom. So next, I swapped rows 2 and 3. Then I used the 3, the initial position in row 2, to eliminate the 1 in row 1 by taking negative 3 row 1 plus row 2 to replace row 1, which gave me this system here. But the problem is I still have 3 variables, x, y, and z. But because I have an all zero row, I effectively only have two equations. Because I only have two equations, but I have more variables, I cannot solve the system for a unique solution. This means that there are infinitely many solutions. So in this case, we would put infinitely many, or INF, for infinitely many. I hope that this has been enjoyable for you and that you have learned to love matrices as much as I have. I've enjoyed having you for this college algebra playlist, and I hope to see you in a future playlist, whether it's trigonometry or calculus 1, 2, or 3. See you down the road.